Hello, everybody. Uh, This lecture we will talk about the psychrometric chart or humidity chart. This chart we talk about the true phase system like air water system. Also, in this case, we have some equilibrium system. We have some phase change from water to vapor, like from vapor to liquid water, something like it. We will talk about the humidity. Like the first term that we talk about the dry bulb temperature. The dry bulb temperature is the FC system of the chart. It is the air temperature measured by thermometer, by thermocouple, by the another conventional temperature measuring device. Like this. If we look at the in abscissa, uh, it is show like the dry bulb temperature. Okay? And the next one, absolute humidity, that I talked you already in the chapter 6 about the absolute humidity. Absolute humidity for this case, sometimes we call like moisture content. Moisture content which is of kilogram vapor, like water vapor and kilogram dry air, which you look at in the y-axis. That's in the y-axis. This is the value of absolute humidity. This is the value of dry bulb temperature. The next term, like relative humidity. Relative humidity is equal to 100 multiplied by pressure of water divided by vapor pressure of water. On the curve, the relative humidity is shown in this curve. This is a relative humidity is 10% relative humidity, 20%, 30%, 40%, 50%, and then 100% relative humidity. We mean the saturation curve at 100 relative humidity. And the dew point is the point at the humid air becomes saturated if it cool at constant. Dew point temperature with the humid air becomes saturated if it cool at constant pressure. How to determine the dew point temperature? Dew point temperature on the psychrometric can easily determine. For example, if we locate air at 29 Celsius and 20% relative humidity, this is at 1 atm, and then you have to move the corresponding curve. You know, like is 29. Right? You know, like the dry bulb temperature is 29 degrees Celsius, and then you drag the vertical line to contact with the relative humidity. Relative humidity is 20%. Okay? But it is 20%. This line for 20%. And then you drag or move the line vertical horizontally to contact the saturation line. This is saturation line, 100% relative humidity. And then you drag the vertical line to the system of the temperature. And for this case, at relative humidity 20% and dry bulb is 29, then you get like the dew point temperature is 4 Celsius. And also, if your system, you know, like the temperature is 29 and absolute humidity is about 0.005, and also you get this. It is 0.005. Okay, you drag the line from 0.005 and contact with the line from the degree Celsius, you get it the same line. And then you drag horizontally to the saturation line and drag vertically to contact with the dry bulb temperature, you get dew point temperature. This you can do the dew point. Another one is humid volume. That's right. Humid volume is the volume that's occupied by 1 kilogram of dry air plus water vapor. That is the cubic meter divided by kilogram. For example, right, for this case, you write humid volume like I showed in the figure. Okay, for this case, it is 0.9, 0.85, 0.8, 0.75. And if you know the humid volume is between 0.85 and 0.9, you can interpolate the value between these two lines. And also, you can interpolate the value between these two lines. For example, if we know the volume occupy about 150 kilogram humid air at temperature 30 degrees Celsius, this would be dry bulb temperature, and relative humidity is 30%. And then you have to drag, right, at 30 degrees Celsius, and relative humidity is 30%. And this point located between 0.85 and 0.9. You have to interpolate between 85 and 9. Maybe it's somewhere 0.87. That's right. 86, 87, 88, 89, and 9. About 0.87. This is the humid volume. That's right. Humid volume. You know humid volume and you know mass of dry air. You can calculate the volume. This is the specific humid volume. Okay, for this case, you get the humid volume is 0.87 cubic meter per kilogram dry air. And also, you know the absolute humidity. About absolute humidity for this case, right? Yes, and also you drag the horizontal line to contact with the humidity, you get about 0.008. It is the absolute humidity. Okay. For this case, you know, right, the mass of humid air is 150 kilogram humid air. Also, you know, right, the absolute humidity. Absolute humidity is 0.008 kilogram water vapor by kilogram dry air. But for this case, the total air is include 1 kilogram dry air plus 0.008 kilogram water. It is mean 1.008 kilogram humid air in 1 kilogram dry air. Right? And also, you know the humid volume is 0.87 cubic meter per kilogram dry air. Then you get humid volume. Humid air kilogram, that's I can say kilogram dry air. So you get volume. It is the example you have to calculate humid volume. From the curve, you get the specific humid volume. And then you multiply with the mass of humid air and divide this by the total mass, the absolute humidity. That's from the absolute humidity. Another term, right? Another term is wet bulb temperature. The wet bulb temperature is the bulb temperature that we use measure by thermometer or thermocouple with over the wick. That's right. Over the wick, and some humid air go across the thermometer that's covered by the humidity. That's mostly when you use this technique, the temperature will be lower than the dry temperature. How to determine the wet bulb temperature? The wet bulb temperature. Wet bulb temperature is humid air depend on both the dry bulb temperature and the moisture content. If the air is saturated 100 relative humidity, no water evaporates from the wet bulb and dry bulb temperature are the same. Yes. So for example, if we would like to use the wet bulb temperature, how to read the wet bulb temperature from the curve? If you know, right, the temperature is dry bulb is 30 degrees Celsius, and you know the relative humidity is 30%. You drag at 30 degrees Celsius to contact with the dry for 30% humidity, and then drag the parallel line to dry bulb temperature constant. That line, this line is the line for enthalpy of saturation. Okay, and then contact with the 100% relative humidity, and then you drag the vertical line. That's like to plot the dry bulb temperature. For this case, you get 18 degrees Celsius. But mostly the dry bulb wet bulb temperature is lower than dew point or lower than the dry bulb. Higher than the dew point, but lower than the dry bulb temperature. For this case, the dry bulb is 30%, wet bulb is 18%. And also, if you would like to determine the dew point, you have to drag the vertical line to contact 100%, get about 11 degrees Celsius. For example, right? This is a wet bulb temperature that you can read from the psychrometric chart. And another term is specific enthalpy of saturated air. In this case, you read from this line, that's the orange line. Yes. What it is determine the entropy from the chart that you follow the constant without temperature line. And you follow the same previously. For the same this. For example, if you know the dry bulb temperature is 25 degrees Celsius, for this case it's not 250, it should be 25, right? 25 degrees Celsius. And then you know the absolute humidity is 0. You for saturation at 25 degrees Celsius, and then you can calculate like the specific enthalpy. For this case, we know the absolute humidity at 0.0202. Okay, we have two conditions. Condition is 25 degrees Celsius, you direct to contact with the line for 0.02 to 0.02 in this. Let me contact at this. Then you follow the parallel line for wet bulb temperature line. This is about 26.5. That's the entropy, specific enthalpy. 26.5. Unit is kilojoule per kilogram dry air. In this case, you also determine based on the previous technique. That's like you based on the reference state. For this curve, the reference state is 0 degrees Celsius, 1 atm for water, and 0 Celsius, 1 atm for dry air. So for this case, we would like to know 1 kilogram dry air at 25 degrees Celsius. Change from 1 kilogram dry air at 0 Celsius to 1 kilogram dry air to 25 Celsius. Right? The first step, you have to calculate delta S air, delta S water. For this case, we have two components, air and water. You change from mass to mole, that like you know the mass of dry air. The dry air, the molecular weight is 29 kilogram per. Then for this case, the temperature change is like 0 to 25, and then you calculate based on integrate 0 to 25 Cp air dt. You get 25 kilojoule. And the next step, we talk about the water. Right? The water is from 0.0202 kilogram water, right, at liquid 0 degrees Celsius to 0.0202 kilogram water at vapor phase at 25 degrees. For this case, we change from liquid to vapor, right, from liquid to. Okay. This is the entropy at vapor at 25 minus entropy at liquid 0 degrees Celsius, which you get out 51.4 kilojoule. How to calculate this? For this case, we have two steps. The first step, you change the temperature from 0 to 25 degrees Celsius. As you calculate it on integrate Cp dt. And the second step, you change the liquid at 25 degrees Celsius to the vapor at 25. Okay. Then you get like the vapor. For this case, there is no like the technique, but for this case, you know like the steam table. It do not necessary to integrate Cp or change from 0 degree to 25 degrees. You know like already from the steam table, you know the vapor, the side is the vapor form at 25 degrees Celsius. You can open the steam table at such vapor 25 degrees Celsius, and then you can open the steam table at 0 degrees Celsius for liquid phase. This set liquid. Then you get enthalpy, because in the steam table, the enthalpy is referent to the triple point. For this case, it's not necessary to integrate CP. But okay, you read from the table, and then you get 51.4, 25.1, and then you calculate the specific enthalpy. It includes the sum of air and water divided by the total mass of dry air. Get 26.5. This is close to the table or to the chart that you read from, or to all the same value. this form. This is a technique how to calculate enthalpy. Next one, the entropy deviation. Entropy deviation. For this curve, we have the entropy deviation of some, for example, it's minus 1.2, minus 1, minus 0.8, minus 0.6, minus 0.4, minus 0.2, minus 0.1, minus 0.05. This is the curve for entropy deviation. Entropy deviation is the same unit of the entropy. Curve are used to determine the entropy of humid air that is not saturated. For this case, if the air or humid air is not saturated, we have to subtract the entropy at the saturation that I showed you previously by the deviation on the unsaturated humid air. Okay. The first step, you have to locate point on the chart corresponding to the specific condition and interpolate to estimate the entropy deviation at that point, and then follow the constant wet bulb temperature line to the entropy scale. For example, for this case, we know the dry bulb temperature is 35 degrees Celsius and 10 relative humidity. About the entropy deviation. In this case, the dry bulb is 35, relative humidity is 10, that's right. And then you parallel or drag the line parallel to the wet bulb temperature. Yes. Then you get the specific entropy is 45. It's 45 kilojoule per kilogram dry. Also, how about the entropy deviation? The entropy deviation is located between the point at 0.4, minus 0.4 and minus 0.6. And then you approximately is about 0.52. 0.4, 0.5, 0.6. For this point is about 0.5. You get the diet deviation, and then you can calculate the entropy of the saturated. The entropy is 45, that's right? 45 and 0.52. Get the entropy of humid air at the condition under saturated. For example, right, I talked to you how to read the value, how to read the table already. For this case, use the psychrometric chart to estimate the first absolute humidity, wet bulb temperature, humid volume, dew point, specific enthalpy of humid air at 41 degrees Celsius and 10% relative humidity. And the second one, amount of water in 150 cubic meter of air at this condition. Okay. For the first step, you have to draw the specified condition at 41 degrees Celsius. This is 41 degrees Celsius. That's 41 degrees Celsius. That's drag to contact with the relative humidity with 10%. This is 10%. It is the point. Right? This point is 10%. This is 41 degrees Celsius crossed with 10% relative humidity. The next step, you can calculate like the vertical line, that's right, to the saturation line. You get about 1, 2, 3 degrees Celsius. This is the dew point temperature. And also you drag the parallel line with the wet bulb temperature like this. And then drag the vertical line, you get about 19 degrees Celsius is the wet bulb temperature. And also you drag further to this, you get the enthalpy at about 54.2 kilojoule per kilogram dry air. That's right. And also for this case, you drag the horizontal line in this axis, you get absolute humidity is approximately 0.0008 kilogram joule per kilogram water per kilogram. And also this point located between minus 6 and minus 8. It approximately is minus 0.7. This is the entropy deviation. That's like kilojoule per kilogram. And also it's located between volume. That's right, humid volume. humid volume, that's right, is about 0.85, 0.9. For this case, it's approximately 0.897. That's it. This is 0.897. I have to integrate between, right? And this now you know all of the value. That's it. You know the absolute enthalpy, you know wet bulb temperature, you know specific volume, you know dew point temperature, you know the specific enthalpy at saturation, and you can calculate specific enthalpy under saturation. You subtract 54.2 by 0.7, you get this value. You get S for specific enthalpy is 53.5 kilojoule per kilogram dry air. And the last, the mole of humid air. You know the volume, that's right. You know the volume is 150. And you know the humid volume is 0.897 cubic meter per kilogram dry air. Right? Per kilogram dry air. And also you know the absolute humidity. Absolute humidity is 0.0048 kilogram water per 1 kilogram. And then you get the humid volume, humid air of the mole, that's right, 0.803 kilogram water. Which gives you the example to use the psychrometric chart. And the next example show you how to apply the psychrometric chart for the material energy. For this case, we balance on the air conditioner or the cooler, that's right. We feed air at 80 Fahrenheit and 80% relative humidity. That's cool to 51 Fahrenheit. That's constant pressure 180. For this case, use the psychrometric chart to determine action of the water. That's condensed, and the layers at which heat must be removed to deliver 1,000 cubic feet per minute of humid air at the final condition. For this case, right, the Q should be negative, but the flow chart we draw the Q is input. Q input is positive because the energy balance that we derive is in terms of Q input. It's positive. And then if you solve for the energy balance, if you get the Q is negative, that's correct, because for this system, the Q is output because the system is transfer Q to the environment, or is the cooling system. Okay. On the basis of 1 pound dry air, for this case, we assume like 1 pound dry air input. And then you have the cooler. For the cooler, you decrease the temperature. If the temperature is decreased lower than or reach the dew point of water, that means the water will drop in the water phase or change from vapor to liquid phase. For this case, we have two products, that's like liquid phase and vapor phase. Okay. First one, phase, we don't know the total mass of the phase. Okay, we denote at M1, is the mass of water vapor. And you know mass of dry air is 1 pound. And you know the temperature is 80 Fahrenheit, humid air is 80%. And then you have to calculate S1, the entropy for it. The second one is also dry air input equal to output. For this case, you get 1 pound mass dry air at 51 Fahrenheit. And we denote M2 as the mass of water vapor. And S2 is the entropy that come out with the dry air output, humid air output. And the last is M3 denote as the pound mass of water liquid. And S3 is the entropy that corresponds to the liquid water. Okay, the first step, you have to check the unknown. We have M1, S1, M2, S2, M3, T, and Q. We have 7 degree, 7 unknown. We have one material balance because for this system we have water and air. You call humid air balance. That's right. And we have true absolute humidity from psychrometric chart, input and output. We know right the entropy from the psychrometric chart, input and output. You know the entropy of condensed from the known heat capacity of liquid, and you know the energy balance. You get 0 degree freedom. The first step, you have to check the property. First one, feed at 80 Fahrenheit Si equal to 80%, then you can calculate S1 and relative humidity, absolute humidity, and enthalpy. That's right. Okay. For this case, you know, 80 Fahrenheit and 80 relative humidity. For this case, you can draw the vertical line to read like that. Absolute humidity is about 0.01 S pound mass water to pound mass dry air. And also you can read for the specific enthalpy is approximately 38.8 BTU per mass dry air. Okay? This is the first condition for the feed. For this case, you know the absolute humidity. You can calculate M1 because M1 is the mass of water, right? Okay. You have the mass of water, but you know the absolute humidity is 0.01 S per mass water per pound mass dry air. But you know for this system, you have 1 pound mass dry air. Okay, you can calculate M2 is the 0.01 S per mass water. And the point 2, output of humid air at 51 Fahrenheit. And you don't know M2, S2. Okay, for this case, the 51 Fahrenheit and saturation. Okay, this 51, this line. Drag to the saturation is the 100 relative humidity. Okay, 100 relative humidity. And read the enthalpy is 20.9 BTU per meter. Yes. And also you can read the absolute humidity is approximately 0.0079 kilogram per water per pound dry. Then you can solve this for M2. M2. That's right. For this case, you know, right, M1 is dry air. You know, the dry air is 1 pound mass dry air multiplied by the ratio or absolute humidity of the water and dry air is 0.0079 per mass water divided by per mass dry air. You get the water 0.0079. And then you can make an balance on water. Water balance, water input equal to water output. We have water output into in humid air in liquid water. There is no generation, no consumption, and accumulation, no. M1 is per mass of water vapor equal to M2 is per mass of water vapor plus MT is the mass of water. You know M1, you know M2, and so for M3. This. You know M1, you know M2, and then you can solve for M3. 0.01 pound mass water per condensate or water condensate. And then you can calculate the fraction of water condensate. How many water is condensate? The condensate of water is MT, that's right. MT is the condensate water divided by water feed. Water feed to the system is 0.018 pound mass feed. You got M1, that's right. M1. You get the ratio of the water. Another is enthalpy of condensation. Enthalpy of condensation. For this case, the system is referring to liquid at 33 degrees Fahrenheit and must be the same condition to calculate it. We have water liquid at 32 Fahrenheit to liquid at 51 Fahrenheit. In this case, we assume the enthalpy of water is approximately 0.75.4 multiplied by 10 power minus 3 kilojoule per mole degree Celsius. That is approximately 75.4 joule per mole degree Celsius. And then you can calculate Cp. This is the term and molecular weight of water and the difference between delta F and delta C. For this case, the unit is per delta C. That's right. 1.8 delta F equal to 1 delta C. Then you change from joule to BTU. And you change pound to gram to pound. You get 1 BTU per pound per degree Celsius. For this case, and then you substitute Cp into the integration term. Because delta S3 equal to integrate 32 to 51 the Fahrenheit Cp dt, and then you substitute Cp, it's approximately 1 BTU per pound mass water. And then you integrate constant, you get T. from 51.30 equal to 115.1 BTU per pound mass water. And then you consider the energy balance equation. The energy balance for no work, no kinetic energy, no potential energy, you get Q equal to delta S. Delta is equal to summation MISI out minus MISI in. That's right. This case. Okay. And then you summarize the table. You have the first column is substance lit, right? Humid air and water in liquid phase. M in, delta S in, right? M in is 1 pound mass. And then you get the humid air in delta S. Is it input humid air? That's right. Is it the feed? S1 is 38.8 BTU per pound mass dry air. And the second one, that's right, output, dry air output, also equal to 20.9. That's 20.9. And also the last one, liquid output. 19, that's right, BTU per pound. Yeah. Okay, and then you can calculate Q equal to delta S, you substitute, that's right, Q equal to 1 pound mass dry air multiplied by 20.9 BTU per pound mass dry air plus 0.01 pound mass multiplied by 16 BTU per pound mass and minus 1 pound mass dry air multiplied by 38.8 BTU pound mass dry air. You get the result is delta S is equal to Q. Q equal to minus 17.7. This is correct because the negative, I mean Q is output of cooling system. Because this equation based on Q is positive from the input to the system. Then you calculate Q, that's right, in terms of the energy rate. That's right. For this case, you know Vs, that's right, equal to 13 cubic feet per pound mass dry air. This you read from the humidity. This from humidity chart. This here. The volume, what is the volume? The volume in the input stream, that's right. 51 Fahrenheit and 80 relative humidity, that's right. 51 Fahrenheit 80, okay, this for read that, and then you can read the image volume is located between this and this, that's right. You get approximately 13 cubic feet per pound dry air. And then the basis is 1 pound dry air, that's right, 1 pound dry air equal to 15 feet per 1 pound dry air. You get V basis is 15 dry air. And for this, you multiply the volumetric flow rate and divide it by the V basis to the Q, you get the heat rate, that's right, 1360 BTU per minute for that case. In the last term, we will talk about the cooling system. Adiabatic cooling. Adiabatic cooling means the cooling process which there is no heat transfer to the environment, that's right. This is the warm gas is brought into contact with a cold liquid. And when the gas contact with a cold liquid happen, the liquid of water will evaporate out, or liquid water vapor will drop or condense to the liquid phase. That's like this for the cool water and hot air. That means the water in the hot air or water vapor will condense to the liquid phase. For example, right, for spray cooling or spray humidification, for this case, the liquid water is sprayed into a relative dry warm air stream. Some of water evaporate. The temperature of air and unevaporated liquid but decrease. right? If the object is to cool the water or the air, the operation is called spray cooling. If the point is to increase the moisture content in the air, the operation is spray humidification. If the moisture increase, we call this spray humidification, right? The second spray dehumidification, that's like the warm humid air is dehumidified by spray cold water into it. And drying the hot air is roll or flow over a wet solid. That's like, for example, over a wet cake deposit in a filter or centrifuge, the water evaporates, leaving a dry solid product. Drying is the last step in the production of more citrulline product, including many pharmaceutical and food product. Okay, the last example is spray drying. Spray drying, a suspension of small solid particles in water is sprayed at a fine mist into a stream of the hot air. For this case, the water vapor or larger solid particles settle out of the air and are removed by a conveyor. And fine suspension particles are separated from the air by a back filter or cyclone separator. Dry milk is produced in this manner. For example, for adiabatic cooling, you can dry the material energy balance on adiabatic cooling operation is straightforward but cumbersome procedure. It can be shown over the if certain well justified as assumption. Yes, we will state them later. And undergo adiabatic cooling to contact with liquid water move along a constant with about temperature line, which is from initial water with 100% condensation. Further, cooling of the air below its saturation will lead to condensation and hence diminution. For this case, if you know the inlet air and then you draw the inlet air parallel to the wet bulb temperature, that's right, to the saturation, and then you get the wet bulb temperature. Operate in the straight line. Right. Okay, for example, right, we have a stream of air at 30%, 30 degrees Celsius, 10% relative humidity is dehumidified in adiabatic spray tower at 1 atm. The emerging air is to have a relative humidity of 40. For this case, the humid air out of the system is 40 relative humidity. And the bottom product is only water. Water input, air input, you have to change. That's right. Okay, the first step determine the absolute humidity and the diabatic saturation temperature of entering air. Use the psychrometric chart to calculate the rate at which water must be added to the humidity. 1,000 kilogram per hour of entering air. And the second one, the temperature of the exiting air. In this case, you follow from the figure. Figure at 30 degrees Celsius, 10% relative humidity for 30. Degrees Celsius. 30 degrees Celsius is this point. With 10% relative humidity, okay, we get the cross line. And then you drag the word horizontal line, you get the absolute humidity is 0.0025 of water to power dry air. And also you can drag to contact with saturation. And right, you drag the vertical line, you get the dew point is approximately 13.2 Celsius. 13.2 Celsius. Okay. About the wet bulb temperature is the saturation temperature is 13.2 Celsius and has a 0.026 kilogram water per kilogram dry air. Then you next state the outlet air. Right? In this case, the outlet air should be located between the starting point and the point at the wet bulb or the saturation line. Intersection, you know, like the relative enthalpy for that case. Okay, for the output air or humid air is 40% relative humidity. Okay, you can operate right at 40% because the 40% cross this line at this point, and then you can drag the vertical line to reach the dew point. Dew point should be 21.2 degrees Celsius. And also at the operating right Second point is SA equal to 0.00631 water per dry air. And then you can calculate mass of dry air. Mass of dry air. So for this case, the absolute humidity is 0.0036 water per kilogram dry air. And then you can calculate the flow rate of dry air. The flow rate of dry air equal to 1000 kilogram per hour. That's right, 1000 kilogram per hour multiplied by the absolute humidity. Right. This for absolute humidity of input is 0.0026. It's 1.0026. 1 kilogram dry air, you get 997.4 kilogram dry air per hour. This is for the outlet inlet equal to outlet. For this case, you calculate based on the inlet property. And the amount of water that must be evaporated in water may be calculated as the difference between the outlet and inlet water flow rate in the air stream. Okay, the water flow rate. We know, right, the mass flow rate of dry air is 997.4 kilogram dry air per hour multiplied by the difference between absolute humidity. That's right, 0.0063 minus 0.0026. That's right. In this case, you get the M water or mass flow rate of water is 3.7 kilogram water. And okay, the temperature at the exit is about 21.2. This is the dry bulb, wet bulb temperature, which equal to the saturation temperature. In general, you can conclude that we have the spray tower air input, which have T1 Celsius, MA, and MW. MA is mass of dry air per second. MW1 is mass of water per second. And water or solid feed, another feed, that's like T2. T1 is feed air, T2 is feed water or solid. That's like out. T3 is air output. The air output is controlled M air, dry mass air. And W plus ME equal to kilogram water per dry per second. That's right. And also liquid, solid. And then if you know CP air, CP water, liquid, and CP water in vapor phase are independent of temperature at prevailing process condition. And the enthalpy change undergo by the unevaporated liquid water and the solid if there is one. It's going to T2 to T4 as are negative compared to the change undergo by the entering waste air and evaporation. Sometimes we can neglect last two terms. The heat requirement to write liquid water from T2 to T3 is negligible compared to the heat of vaporization water. If the energy balance equation delta S equal to 0 is written for this process. These three assumptions are made for the required equation. That's right. MaCpa T3 minus T1, MWaCpH2 water T3 minus T1, and M water delta S vapor to that's right equal to 0. And then you can rearrange divided by Ma. MW divided by Ma, you get this equation. And apply this for this cooling system. We will stop the lecture for this.